there are different ways of multiplying vectors. Let's compare the properties of the dot product, cross product, and scalar triple product. Dot product takes two vectors in Rn. By input, I mean whatever we're putting into that vector operation. The n refers to the number of dimensions or number of components. For example, the vectors can be in 2 dimensions, so 2 components, or 3 dimensions, 3 components, and so on. The operator of the dot product is the dot operator. Here we have u dot v. It's ambiguous to say u times v or u multiplied by v because there are different ways of multiplying vectors. To be specific, we should say, in this case, u dot v. To do the dot product, multiply the corresponding components of either vector and then add together these products. The formula says, multiply the first component of u with the first component of v, second component of u with the second component of v, and so on, for however many components there are. Another way of finding the dot product between two vectors is by multiplying the magnitude of one vector with the magnitude of the other vector, and then multiplying by the cosine of the angle between these two vectors. And the result of a dot product is a scalar, it's just a number. Cross product works differently. Cross product takes two vectors in R3, so these vectors each have 3 components. As a side note, I think cross product is defined for higher dimensions, but we're just going to focus on 3 dimensions in this case. If we're doing a physics problem in 2 dimensions, it is still kind of possible to do a cross product of the vectors. The third component of either vector will be 0. The operator of the cross product is the multiplication sign. U cross v is evaluated as a determinant. The first row has the standard basis vectors in the x direction, y direction, and z direction. Then we put the components of the left vector in the middle row, and the components of the right vector in the last row. When we do this determinant, we're going to get a number multiplied by I hat, a number multiplied by j hat, and a number multiplied by k hat. These correspond to the components in the x, y, and z directions, respectively. So it's interesting that from a cross product, we actually get a vector, which is different from a dot product, which produces a scalar. A different formula for getting the magnitude of the cross product, so note that it's just the magnitude, not the vector form of the cross product. We multiply the magnitude of u by the magnitude of v with the sine of the angle between these two vectors. This formula is slightly different from the dot product formula. Dot product has cos, but cross product has sine. The cross product of 2 vectors is also a vector. Now the neat thing is that this cross product is actually perpendicular or orthogonal to the starting vectors, u and v. The scalar triple product is like a combination of dot product and cross product. Scalar triple product, triple as in 3, means that we're going to take 3 vectors, and these vectors are in R3, so still 3 dimensions. We're going to have a dot operator and a multiplication sign. In this case, we have the vector w that's dotted to the cross product of u cross v. And we evaluate the scalar triple product as a determinant. The left vector, we put its components on the first row, the middle vector components in the second row, and the right vector in the third row. And we just do cofactor expansion, we just evaluate this 3x3 determinant, and the answer is going to be a scalar. We can also do the scalar triple product in 2 steps. Start with the stuff in brackets, do u cross v first, and then dot that result with w. Let's summarize the order or the sequence in which we do these vector products. With a dot product, the order doesn't matter. U dot v is the same as v dot u. Cross product is anti-commutative, which means u cross v is the negative version of v cross u. Geometrically, it looks something like this. We can use the right-hand rule to figure out the direction of the cross product. If we go u cross v using the right hand and curling your fingers from u to v, your thumb will point in the direction of the cross product. In this case, it's pointing upward. However, if we go v cross u, we still use the right-hand rule, then curl the fingers from v to u, and then the thumb points downward. So v cross u is actually down instead of up. Whether we go u cross v or v cross u, the cross product will point in opposite directions. The scalar triple product is evaluated as a determinant, so the properties of the determinant will apply. Every time we swap two vectors, we're going to swap two rows, and swapping two rows will multiply the determinant by -1. So then each swap of two vectors will multiply a -1 to the value of the scalar triple product. Starting with W dot in brackets U cross V. If we switch W and U, let's say U dot in brackets W cross V, it's a swap of two vectors. So then the answer from the scalar triple product will be the result from WUV and then just multiply by -1. Multiplying vectors is different than multiplying regular scalar numbers because vectors have a direction, and the direction or orientation of the vectors also affect the value of the product. The formula from above for U dot V has a cos theta factor. Theta refers to the angle between the two vectors. When the vectors are orthogonal, perpendicular, at right angles or 90 degrees or 𝗦/2 radians from each other, however we want to say it, the cosine of 90 degrees or 𝗦/2 radians is equal to 0. In this formula, we have magnitude of U multiplied by magnitude of V multiplied by cos 𝗦/2, which is 0, then U dot V is equal to 0 when these vectors are orthogonal to each other. The cross product can be evaluated as a determinant. According to the properties of determinants, when two rows are proportional to each other, proportional meaning scalar multiples of each other, then the determinant evaluates to 0. So then if two vectors are parallel or anti-parallel, they're scalar multiples of each other, then the cross product will evaluate to 0. Using the formula from above, when the vectors are parallel pointing in the same direction, the angle between these two vectors is 0. If the vectors are anti-parallel pointing in opposite directions, the angle between anti-parallel vectors is 180 degrees, or pi radians, and sine of 0 or pi is 0. Putting this into the formula from above, for the magnitude of the cross product, we have magnitude of U multiplied by magnitude of V multiplied by 0, so then the magnitude of this cross product is going to be 0. We have the same idea with the scalar triple product. Since the scalar triple product can be evaluated as a determinant, then having vectors that are parallel or anti-parallel will give us proportional rows in the determinant, and the determinant in scalar triple product will evaluate to 0. We have an interesting contrast here. Dot product, when vectors are orthogonal, evaluates to 0. Cross product and scalar triple product, when vectors are parallel or anti-parallel, then they evaluate to 0. Going back to the dot product, when vectors are anti-parallel, the angle between these vectors is 180 degrees, or pi radians, and the cos of pi is -1. Putting this factor into the formula for dot product, we're going to have magnitude of U multiplied by magnitude of V multiplied by a -1, which is the opposite of what happens when these vectors dotted together are parallel, when the angle between these vectors is 0. Cos of 0 is +1, and so the dot product looks similar to when the vectors are anti-parallel, it's just that we have a positive sign instead of a negative sign. Another way of thinking about this is to focus on the cosine. Cosine oscillates between -1 and 1. When cosine is -1, we get the negative version of this dot product. When cosine is +1, we get the positive version of this dot product. And then work backwards. Figure out at which angle is cosine -1 or +1. Cosine is -1 when the angle is pi. Cosine is +1 when the angle is 0. The smallest magnitude we can get from a cross product is 0, which corresponds to the 0 vector. And we get the 0 vector when the vectors crossed together are proportional to each other, so which goes back to the previous case. To get the maximum magnitude from a cross product, the vectors crossed together have to be orthogonal. The angle is 90 degrees, or 𝗦/2 radians, and sine of that angle is equal to 1. Then the maximum magnitude of a cross product is equal to the magnitude of U multiplied by the magnitude of V. Another way of thinking about this is to focus on the sine theta. Sine oscillates between -1 and 1, and in order to get the maximum sine equals 1, the angle has to be 𝗦/2. With the scalar triple product, the minimum magnitude is 0 for the same reason as with the cross product. When vectors are proportional to each other, the scalar triple product evaluates to 0. If none of those vectors are proportional to each other, we're going to get either a positive number or a negative number, but the magnitude is not going to be 0. If having parallel vectors will minimize the magnitude of the scalar triple product, then we're going to do the opposite. Having input vectors that are all orthogonal to each other will maximize the magnitude of the scalar triple product. Just to get a mental image of what it looks like to have 3 input vectors that are all orthogonal to each other, we can fit a square between each pair of vectors, a square between w and v, w and u and v. Sometimes a sketch is useful to see what's going on and visualize the orientation of these vectors relative to each other. It doesn't matter the length of these 2 vectors, as long as the length of these vectors are non-zero. We're just focusing on how the orientation of these vectors relative to each other will affect the product. Antiparallel vectors, meaning that the vectors point in opposite directions. The angle between these vectors is 180 degrees, or pi radians. Cos of pi is -1, so the dot product will be negative. However, sine of pi is 0, the cross product will evaluate to the 0 vector, and also has a magnitude of 0. When the angle between these 2 vectors is obtuse, meaning the angle is greater than 90 degrees but less than 180 degrees, or greater than pi over 2 and less than pi, cos of the angle is a negative number, which means the dot product will be a negative number as well. When the vectors are orthogonal or perpendicular to each other, the angle is 90 degrees or pi over 2 radians. Cosine of this angle is equal to 0, which means that the dot product is also going to be 0. When the angle is acute, the angle is greater than 0 but less than 90 degrees, or less than pi over 2 radians. The cosine of this angle is a positive number, so the dot product is also positive. When the vectors are parallel, they point in the same direction. The angle between these 2 vectors is 0. Cos of 0 is +1, so the dot product is a positive number. Sine of 0 is 0, so the cross product evaluates to the 0 vector, which has a magnitude of 0.